first of all, I think it would be useful to investigate the 3 meter per second to 6 meter per second over a 2-second interval to see what's going on there. So if the belt speed V, and this is question 122, the belt speed V is changing over time from a value of 3 meters per second to 6 meters per second in 2 seconds. And it says uniformly. Okay? So you can see then that here we have a speed or velocity of the belt versus time graph. Then being that this is at a linear function, then the slope of that is going to be an increase of 3 meters per second acting over 2 seconds. So we have V over T. This is going to be the average acceleration then, which they told us is going to be constant, is that net change is going to be 3 meters per second per 2 seconds. So we end up with 1.5 meter per second squared. Tangential acceleration. Tangential along the belt. So think about it when you read the problem, and then see if you can pin down the component that this happens to be, which happens to be tangential, because that's the belt, that's the rate at which the belt speed is changing. Okay, so that's a useful piece of information. This little sketch is not a bad thing to include. You can real clearly see this or explain this to someone else then if you do that. Always try to include a sketch if you can, if the information allows it. So now, we come up there onto that camshaft sprocket, and it's sitting up there like this, and then the belt comes down along here, and this is a 60 millimeter radius. So I'm going to change that so I don't screw up the problem. 60 millimeters is 0.06 meters, right? Because it's 0.060, and you kick the decimal over, right? So we have that radius on that camshaft sprocket, and they were interested up on here somewhere, so I could just take this point of tangency as the point of interest. And so what could I put on my picture based on what we've already talked about?
Tangential acceleration.
I could put that tangential component of acceleration on there, which happens to be this constant 1.5 reading. So that's kind of handy. Now,
doesn't the belt go the other way?
Yeah, it does.
oh, it does?
Yes.
Oh, darn. Okay.
It's just these swings always.
So I'm going to turn it around. I didn't see which way it was spinning.
You don't even know what these swings.
This thing's going this direction, so therefore we have this tangential term here pointing that way. And this is P1 or P2? P1. P2 is out here on the belt. What's P2 carrying?
Just
That same tangential acceleration.
Ah, that same tangential acceleration. 1.5 meter per second squared.
There's no reason in geometry of this problem to suspect that that tangential acceleration differs throughout the belt at all, correct? It can't.
It's tangential.
unless the belt punches up.
It's telling us that it remains constant, doesn't it? Because of this linear profile. You know,
Throughout the entire belt.
they describe that to us.
So just looking at this, since P2 is going straight, can't you just say that that's the magnitude of full acceleration?
Yeah, it's not curving.
Yeah, and you're suggesting that P2, this is the magnitude of the acceleration, which means that this is the acceleration?
Yeah, because
And
there's
how else could you explain this to somebody that indeed has to be it?
no
Look at the
curve.
path.
It's straight, it's not.
It's a straight line path. There is no tendency, there's no curvature to the path. An infinite radius of curvature. Infinite radius of curvature. So therefore, think about that. What's that normal thing? And let's see, if we went to the original v squared over r, v squared over infinity is 0, right? So the normal acceleration, v squared over infinity, heads towards 0. So that sort of is the way of explaining that. Now, what I forgot to write down or even look at is what are we supposed to solve in this problem?
The magnitudes of the accelerations of both points halfway through the time interval.
Okay, so we're looking at 1 second then, okay, right? At t equals 1 second, we're looking for the magnitude of the acceleration of P1 and P2. I usually write this down before I even start playing with the problem. I usually write down what am I looking for on there in an abbreviated form. I mentioned this previously also, is try to synthesize the problem in an abbreviated form without writing all the verbiage out, but enough information so that you wouldn't have to open up the book maybe to look at your work and understand it. I don't have quite enough of that information here on this layout to do that, but it's adequate for talking purposes. So, P2, looks like we nailed P2, didn't we? Didn't we just finish that?
1.5 meters per second.
Yeah, and doesn't that slope remain constant even here at 1 second? See, here's the point of interest right there at 1 second. Here's our point of interest for this problem. And so at P2, we've got it done. So this implies then that the acceleration at P2 is equal to this 1.5 meters per second squared when t is equal to 1 second. So there's the answer to that. Okay? We come back up to P1. Is it the same answer
No.
for the acceleration?
It's got a normal component.
Oh.
Got the normal
Once you get onto the belt, once you get onto this camshaft or this cam sprocket, you're now on circular motion. So it's now on a curved arc. So you have a normal acceleration here at P1. Normal acceleration at P1. And we have to figure that thing out. We could, now I want to belabor this a little bit, just humor me for a second. We could write this equation for the speed. Speed is equal to, what is it? Slope is 1.5 t plus 3, right? At 1 second, this is going to be 4.5 meters per second, right? Why did I say humor me? Let me do some algebra. Would you have done algebra on it? No, you would have looked at the 3 and the 6 and taken the average of the two because of the linear behavior.
Right.
But there are a whole lot of profiles that are not linear, okay? And you would have to then use your either curve fitting abilities to match a certain type of function through there that you need to in a design, and you may then have to actually develop the equation of that profile to be able to determine the speed at a certain location. Make sense? Okay. So then, with this piece of information now, we're looking for this acceleration at P1, and so this is equal to what? So we have that the normal acceleration at P1 has to be equal to v squared over r. We have our speed here, substituting 4.5 squared over the radius of the cam, 0.06. And somebody punch that out.
337.5.
Yep. Excuse me, what is it?
337.5.
Meters per second squared. So we have that component, and our tangential component at P1 is the constant 1.5.
Wow.
Square root of the squares.
Square root of the sum of the squares, and the answer is going to be
About 3.7.
that guy. So the normal's the one that's really kicking it, right? Even though the belt's speeding up, the normal's the one that's really kicking it. Okay. So the answer to that normal acceleration, or I'm sorry, the total acceleration at P1 is going to be the square root of the sum of the squares of these two components. And that should agree with, I don't know if I can read my writing there.
Yeah,
It's pretty much the
it's
same.
pretty much the same thing. There's only
238,
within the
yeah.
significant,
Because the 1.5
figure
doesn't
range of the
do
book, it's the
much.
same
338, if you guys, if you round that off,
nominal,
Yeah.
meters per second squared.
what we want.
Okay. Relatively straightforward problem involving normal tangential path-dependent coordinates. Okay, we've got about 20 minutes left. What I'd like to do today is now introduce to you the polar coordinate approach, and then we can you can sort of see how it ties to how it ties in with the normal tangential. All right, so let's go through the theory on that, and that probably will take care of us today. Any questions in summary before we move on here? Okay. Polar coordinate kinematics. Polar coordinate kinematics. Okay, let's go back to something familiar. We have a path, some kind of a two-dimensional path. We have a position vector that gets us to a point on the path. And what we want to do, and we've seen this described in rectangular form. X, I, Y, J. X, I, Y, J for that position vector. And we feel pretty comfortable with that. Right? Okay. Pretty simple. Polar's even simpler. Polar coordinates, remember, are defined in terms of some distance from the pole, some r, magnitude, and some defined angle with respect to some reference axis. So this polar position right here could be described as r theta in space, just as well as describing it in rectangular as xy. If we now define a unit vector, just like we did I and j, we now define a unit vector that points in the pole, in the direction from the pole to the point of interest. It's going to point out radially from the pole. And we can just define that as a unit vector. Now the direction of that thing is going to change as this particle moves along a path. The direction of that's going to change, as well as oftentimes the length r. Feel good? So that's where we start. The position vector in polar form is defined as the distance from the pole times a unit vector in that radial direction. Radial direction. And you kick the camera a little to the right. There we go. All right? This is it. This is simpler than that. If I tell you the direction of the unit vector and then I ask you to go out there 40 meters, you've got it. Okay. So there's the first part of our kinematics. We got the position, as long as we know that direction of that thing. Now we have to differentiate this, because we know that the time derivative of that position vector is going to be the velocity vector. We did that derivation the other day. So the velocity then is going to be the time derivative of the position vector. And now we have two time-dependent functions here. R's magnitude could certainly change with time, and the direction of that unit vector could change with time. So again, similar to what we had to do with the normal tangential stuff, we have to crank the derivatives on both of these through the product rule. So we have r dot r hat plus r times the time derivative of r hat. And I mix Newtonian and Leibniz notation there. How are we going to figure this thing out? Remember what we talked about the other day, previous session? Let's go back. Let's see. Remember the other day we had speed v in the tangential direction, and then we let a little bit of motion occur and that tangential direction changed. And we worked up the derivative of the tangential unit vector with respect to time. We have to do the same idea here. So, at a particular instant, r hat is pointing that way. After a little bit of motion, a differential amount of motion on ds along this arc, r hat is now rotated through a slight rotation angle. We called that just the other day d beta, differential rotation angle. And in the limit, this change in r hat right out here, this delta r hat, is a dr hat, which in the limit is perpendicular to r hat, perpendicular to r hat, and it's in the direction of increasing theta. It's in the direction of increasing theta. Okay? I've defined this way counterclockwise for increasing theta, and if I let the particle move along a path that direction, then as I move through a differential angle change, d beta or d theta, I could call it d theta as well, then in that normal direction to this is a vector that we're going to define as a unit vector called theta hat. So the direction of this dr hat is this way, and that's that we just call, that direction is theta hat. All right. What's the magnitude of this dr hat?
The magnitude of the whole
Of this thing, which is 1 times its theta angle rotation which, and I'm going to change my symbolism here, because if I let, back here on this picture, if I let this angle change slightly through an angle change here, d theta, the particle's now in a new position up here, and the rotation that's occurred on the r hat is that d theta. Julie?
I don't understand how you know that dr hat is 1.
Is what?
Is 1. Oh.
It's a unit vector,
Oh, everything.
magnitude 1, right? That's 1 in
I
the
guess
r
what's
hat.
confusing is what is it always only going to move a unit of 1?
Well, no, the length of the unit vector is always 1, just like I hat and j hat. Those things are always of magnitude 1.
Yeah.
But what happens is that it rotates a little bit. So this length is 1 physically, and that thing is 1 physically in length. And so it's in essence what we're really doing here. Let me exaggerate a little bit.
Okay.
It's a circular arc. And the angle here is d theta. That's 1. So that arc length right there is 1 times d theta, r times d theta.
Okay.
Okay? And so that's d theta. And so that arc length right there is d theta times 1. And this thing is in that particular direction, so I have to assign a direction to this scalar here. And that direction happens to be theta hat. Now, if I divide by differential time, you can see that dr hat dt is then equal to d theta dt times theta hat. We oftentimes write that as the time derivative of r hat with respect to t is equal to theta dot theta hat. So it started out real simple. Our position vector is r times r hat. And then you crank the time derivative and it gets a little more sophisticated. And this now turns into our velocity expression, which we use a lot, r dot r hat plus r, replacing this with theta dot in the theta hat direction. So this is the velocity described with a radial component of velocity, v sub r, r hat, and a theta-directed component of velocity, v sub theta. So this is the way we define the velocity vector in polar coordinates. Yes?
So the theta hat isn't a normal unit vector in the sense the ones that we're used to seeing. It's just
It is.
an angular.
No. It's in a direction that is perpendicular to r hat, always. Theta hat's always perpendicular to r hat, okay? And it's in the direction of increasing theta. It's defined as in the direction of increasing theta. So it's always going to be perpendicular to r hat, as you see illustrated here, and always in the direction of increasing theta. You can take your index finger and thumb and do that and see it, r hat, theta hat. And those unit vectors just stick with the particle as the particle moves on its path. Okay? Now, this is interesting. What is this r dot? What is r dot? The speed toward or away the pole. Toward or away from the pole. That's what I like to call the telescoping kind of effect. Is the distance r increasing, moving away from the pole, or is it decreasing, coming back towards the pole? Okay. This term is in the theta direction. So you can split your velocity up. Check this out. If this is the velocity now, let's say I draw it kind of short. We know the velocity is tangent to the path. I can split that into two components. One right there, which is your r dot term. This drawing's getting a little messy. Here's your r dot term. Right there. And this term right here, that component right there, here's your speed, your velocity over there, and you break it into two orthogonal components, and here is your r theta dot term, perpendicular to r dot. Okay, and I've got 5 minutes left. I want to get the acceleration for you. Okay? Now, look at this. We have time-dependent functions in both cases here and in 3 cases there, don't we? So the next derivative gets a little more exciting. And notice what's going to show up. We're going to see our dr hat dt show up again, aren't we? This thing is going to show up again when we crank the next derivative here. And we're going to have to see what d theta hat dt looks like. Same kind of a deal as we just did here. And so what I'm going to do is I'm going to work on that guy first. So here's theta hat. And then I'm going to let it rotate through a little differential angle as it rolls. And here's the d theta hat. And here's our theta hat term right there. Okay. And the angle rotation right there is d theta. So the value of this thing out here is going to be 1 times d theta. And look at its direction. What direction is this, folks? Perpendicular to the theta hat, coming back this way. It's back towards the pole, isn't it? Isn't this pointing back towards the pole?
Yeah, it's negative r hat.
In the negative r hat direction. So this little unit, this little d theta hat vector right here pointing that way is this magnitude in the negative r hat direction. So d theta hat dt is going to be equal to, dividing by dt here, equals minus theta dot r hat. So keep that thing in mind for a second as we crank the derivative here, and I just got 2 minutes to do it. Okay, so here we go. The acceleration is going to be r double dot dr hat dt plus r dot theta hat plus r theta double dot theta hat plus r theta dot d theta hat dt. Oops, I screwed up. My first term here, I did 2 derivatives at the same time, so I need a little extra space. In the interest of time, I'm going to just fix that. So I get r double dot r hat plus r dot dr hat dt. So I get all these terms. Got 2 minutes left. See, they should hold up cue cards back there in the room and tell me how much time I have. Okay, so let's see what we have. This thing turns into theta dot theta hat, and this thing turns into minus theta dot r hat, right? And if we now look for the r hat terms, here's an r hat term, r double dot, and here's an r hat term, this stuff, see it? Minus r theta dot squared. Those are our r hat terms. And if we add to that the theta directed terms, we have one right here. We have an r dot theta hat, and we have an r dot theta hat. That's two of them. And then we also have this guy right here, r theta double dot. So we get r theta double dot plus 2 r dot theta dot terms, and that is our theta directed component. So here's the acceleration made up of a r-directed acceleration term and a theta-directed acceleration term right there. Sorry for the compressed notes. What we'll do tomorrow or the next class session is we'll investigate what each of these parts mean, and we'll actually work some problems out involving them and answer questions you might have from previous material.
What homeworks due Thursday?
Thursday, what would be reasonable? Assignments, first three assignments maybe?
1, 2, 3. Okay.
Any one of those? I'll just grab one of them from you. Okay? So have them ready to go, separate pieces of paper. Thanks a lot. Okay.
No Stevens.
No statements.